Long before there was a sun, our neighborhood in the Milky Way existed as a cold and almost invisible cloud of gas and dust. This cloud drifted through darkness for millions of years, carrying the raw material that would eventually become every world we know. It held mostly hydrogen and helium, the simple elements left behind by the earliest generations of stars. Mixed into that gas were tiny grains of carbon, silicates, metals, and ice, forged in older stars and scattered by stellar explosions. Those ancient grains carried a history that began before the sun and survived inside meteorites that still fall on Earth today. The cloud was not empty or smooth, but threaded with faint turbulence, magnetic fields, and pockets where matter gathered more densely. Gravity was already at work, quietly pulling every atom toward nearby atoms and testing whether one region could begin to collapse. For a long time, pressure and motion resisted that pull, keeping the cloud suspended in a fragile balance. Then something disturbed the darkness and tipped part of the cloud beyond the point where gravity could be stopped. Scientists cannot identify the exact trigger, but several possibilities fit what we observe in star-forming regions today. A nearby massive star may have exploded, sending a shockwave across space and compressing the cloud along its path. The expanding bubble of a hot young star could also have pressed into the gas and gathered it into a denser shell. It is even possible that ordinary turbulence created the dense pocket without any single dramatic event. Whatever the cause, a small part of the cloud became heavy enough for its own gravity to take control. The future solar system began not with a bright flash, but with a silent inward fall across an immense region of cold space. As the region contracted, gravity pulled more gas inward, increasing its density and strengthening the very force driving the collapse. This created a runaway process in which falling matter made the center heavier, and the heavier center pulled matter in even faster. The collapse did not happen from one edge to another like a falling wall. Instead, countless streams of gas moved inward along twisting paths, colliding, bending, and feeding a growing center. The cloud also carried a slight overall rotation, inherited from random motions and interactions long before the collapse began. That tiny rotation became increasingly important as the cloud shrank. Like a skater pulling in her arms, the collapsing material spun faster as its mass moved closer to the center. Conservation of angular momentum turned a gentle drift into a broad, rotating structure around the newborn center. Material falling directly toward the middle could continue inward, while material moving sideways resisted a straight plunge. The result was a flattened disk, wide enough to contain the raw ingredients of the sun, planets, moons, asteroids, and comets. At its center, most of the mass accumulated into a dense, hot object that had not yet become a true star. Astronomers call such an object a protostar, a stellar embryo still growing by pulling material from its surroundings. The young protostar was buried inside dust, so no distant observer could have seen it shining in visible light. Its energy escaped mainly as infrared radiation, warming the surrounding cocoon while the collapse continued. Modern telescopes find many similar systems in nearby stellar nurseries, allowing scientists to study different stages of the same process. These observations do not show our own past directly, but they reveal how stars and disks are forming across the galaxy today. By comparing hundreds of young systems, researchers can reconstruct a sequence that no single telescope could watch from beginning to end. The disk around the early sun was not a quiet ring of neatly arranged material. It was a turbulent environment where gas spiraled inward, dust collided, magnetic fields twisted, and energy moved in every direction. Some regions became hotter as they approached the protostar, while outer regions remained cold enough for ice to survive. This temperature gradient would help decide which materials could become solid at each distance from the forming sundae. Close to the center, heat destroyed fragile ice and left behind substances that could withstand high temperatures. Metallic iron, nickel, and rocky silicate grains were among the solids available in the future realm of the inner planets. Farther out, water, ammonia, methane, and other volatile compounds could freeze onto grains and add far more solid mass. The boundary beyond which water could remain frozen is often called the snow line or the frost line. Its exact location changed as the young sun brightened and the disk evolved, so it was never a perfectly fixed border. Yet the general contrast between the hot inner disk and the cold outer disk profoundly shaped the kinds of planets that could grow. The disk was enormous by human standards, but remarkably thin compared with its width. Most material orbited near a common plane because repeated collisions canceled motions that pointed too far above or below it. Over time, the system became flatter, although the gas remained restless and the disk continued to ripple, warp, and churn. The early sun and its disk formed a single connected system, constantly exchanging mass, heat, and angular momentum. Magnetic fields may have helped channel gas toward the protostar while launching some material away in narrow, powerful outflows. These jets carried energy and angular momentum outward, helping the central object continue to gather matter. At the same time, radiation from the protostar warmed the inner disk and altered the chemistry of dust grains passing nearby. Some grains were melted and cooled again, preserving evidence of sudden heating events in the oldest known solar system material. Meteorites contain tiny round objects called chondrules, many of which were once molten droplets in the young disk. Other inclusions formed at extremely high temperatures and rank among the first solids created after the collapse began. By measuring radioactive isotopes in ancient materials, scientists can estimate when the solar system began to form. The oldest dated solids formed about 4.567 billion years ago, near the opening moments of the disk. This date is not the birthday of every planet, but it provides a reliable starting point for the story of the solar system. Once solid grains existed, the next challenge was to turn particles smaller than sand into bodies large enough for gravity to dominate. Gravity between individual dust grains was far too weak to begin that process by itself. Instead, grains met gently and stuck through electrical forces, surface effects, and the thin coatings that covered some particles. Each successful collision made a slightly larger cluster, increasing the chance that the cluster would meet and capture more grains. But growth was not simple, because faster impacts could shatter fragile clumps or make them bounce apart. The disk therefore acted like a vast laboratory, where countless collisions tested which shapes, speeds, and materials could survive. Some models suggest that fluffy aggregates could grow by absorbing impacts rather than breaking, like compact stones. Ice beyond the snow line may also have helped particles stick, giving the outer disk an important advantage in building larger bodies. As clusters grew, they settled closer to the disk's central plane, where the concentration of solids became even greater. The densest bands of particles may have become unstable under their own collective gravity and collapsed into larger objects. Scientists are still working to understand exactly how the first difficult steps from dust to planetesimals occurred. No single mechanism has solved every problem, and different pathways may have operated in different regions of the disk. Yet meteorites, laboratory experiments, and computer simulations all indicate that growth from tiny grains was possible. Once objects reached roughly kilometer scales, their gravity began to matter more strongly during encounters. These bodies are called planetesimals, the small worlds that served as basic building blocks for planets and many moons. They were not all alike, because each region supplied a different mixture of rock, metal, organic material, and ice. Near the Sun, planetesimals were mostly rocky and metallic, while distant ones could contain large amounts of frozen water. Their orbits crossed, their speeds changed, and their collisions ranged from gentle mergers to violent destruction. Every merger altered the local balance, creating larger targets that could draw in smaller neighbors from a wider region. Growth accelerated where material was abundant, but it stalled where collisions removed bodies faster than new ones could form. The future planets began as uneven swarms, not as orderly spheres waiting in their modern orbits. Many planetesimals would later be shattered, swallowed, or thrown away, leaving only fragments of their original population. A few survivors still circle the sun as asteroids, comets, and distant icy bodies, preserving clues from the earliest era. They are not untouched fossils, but their chemistry and structure retain records that planets have largely erased through heat and geology. The disk was now filled with embryos of possibility, from dusty clumps to planetesimals already large enough to reshape nearby space. At the center, the protostar continued contracting until its core became hot and dense enough for hydrogen nuclei to fuse. Fusion marked the true birth of the sun, releasing energy that pushed outward against the continuing pressure of gravity. The newborn star did not become calm immediately, but its ignition changed the future of every object remaining in the disk. Light, heat, stellar winds, and radiation began clearing away gas while the young worlds continued to grow from what remained. For several million years, the disk still held enough gas to influence orbits and to feed the largest objects forming far from the Sunday. Gas could slow small bodies, bend their paths, and carry drifting solids toward regions where they might become trapped. Spiral waves and pressure variations created temporary lanes, gaps, and rings that concentrated dust into brighter bands. Astronomers now image similar ring disks around young stars, although a ring does not always mean that a planet already exists. Some rings may be sculpted by planets, while others can arise from changes in temperature, chemistry, or gas pressure. The young solar system probably contained structures that came and went as matter flowed through the disk. Nothing about this environment was permanent, yet every temporary pattern could change which particles met and which bodies grew. Meanwhile, the sun's growing brightness gradually moved the snowline outward and then inward as the disk thinned. Materials that had once been stable could evaporate, travel with the gas, and later freeze again in a colder region. This mixing helps explain why meteorites can contain materials that formed under very different temperatures and conditions. The early disk was therefore both a birthplace and a conveyor, moving matter while transforming it through heat and collision. Around it, the first chapter of solar system history was ending, and the age of growing planets was about to begin. The young sun now shone above a disk crowded with countless bodies, each following a path shaped by gravity, gas, and collision. Most were still small, but a few had already begun to gain an advantage over everything moving nearby. Their growing gravity reached beyond their physical surfaces and bent the paths of smaller planetesimals toward them. The age of simple dust growth was giving way to a faster and far more violent stage of planetary construction. When two small planetesimals approached, they could easily miss each other or collide at an angle and break apart. A larger body changed those odds because its gravity pulled passing objects inward and made direct impacts more likely. Each successful impact increased its mass, strengthened its gravity, and widened the region from which it could gather material. This accelerating pattern is called runaway growth, because the largest bodies could briefly grow much faster than their neighbors. The process did not produce one winner that swallowed the entire disk. Instead, many growing bodies emerged at different distances from the sun, separated by regions they increasingly controlled. As they became more massive, they stirred nearby planetesimals into faster and more tilted orbits. Higher collision speeds slowed the advantage of runaway growth and pushed the disk toward a more balanced competition. The largest objects entered a stage known as oligarchic growth, when several dominant bodies shared each broad region of the disk. Each one consumed smaller material from a feeding zone surrounding its orbit, while avoiding equally powerful neighbors. Over time, these growing objects became planetary embryos, bodies comparable in scale to large moons or small planets. The inner solar system may have contained dozens of such embryos moving among vast numbers of leftover planetesimals. Their orbits were not yet the nearly circular and widely separated paths followed by the planets today. Embryos pulled on one another, exchanged energy, and gradually developed paths that crossed through overlapping regions. Some encounters ended with a gravitational deflection, while others ended in collisions powerful enough to reshape entire worlds. Planet building had become a contest between accumulation, fragmentation, scattering, and survival. Large impacts released extraordinary heat, melting rock across wide regions and sometimes creating global oceans of molten material. Radioactive elements also produced heat from within, while continued compression warmed the interiors of growing bodies. Once enough material melted, dense metals sank toward the center as lighter rocky substances rose above them. This separation created metallic cores, rocky mantles, and early crusts within some of the first substantial worlds. The process is called differentiation, and it transformed mixed collections of primitive material into layered planetary bodies. Differentiation erased parts of the original chemical record by moving elements into different depths and mineral environments. Small objects that never fully melted preserved more primitive mixtures and later survived as valuable fragments inside meteorites. Together, layered worlds and primitive remnants reveal two very different outcomes of the same early disk. Near the Sun, only limited amounts of rock and metal were available for building planets. Mercury, Venus, Earth, and Mars, therefore, began from a relatively thin supply of solid material. Their ancestors could not easily capture hydrogen and helium because the inner disk was hot and their gravity remained modest. They grew mainly as rocky worlds, assembled from metals, silicates, and smaller amounts of volatile rich material. The four inner planets did not simply appear in their final sizes at four predetermined locations. Computer simulations suggest that many embryos collided over tens of millions of years before only a few major planets remained. Some material fell into the Sun, while other bodies were thrown outward or shattered into smaller pieces. The planets that survived were the outcome of one complicated sequence among many paths that might have been possible. Beyond the snow line, the situation was different because frozen water added greatly to the supply of solid material. Ice mixed with rock and metal to build planetesimals that could grow more quickly than many bodies closer to the sunday. Some embryos in this region became several times more massive than Earth before the surrounding gas disappeared. That timing was critical because the great gaseous planets could form only while the disk still contained abundant hydrogen and helium. The leading explanation for Jupiter begins with a heavy core assembled from rock, metal, and ice. As that core grew, its gravity began holding a thick atmosphere drawn directly from the surrounding solar nebula. At first, the atmosphere gained mass slowly because heat from falling material resisted rapid contraction. When the envelope became sufficiently massive, it could cool and contract faster, allowing far more gas to fall inward. Jupiter then entered runaway gas secretion, a brief period when its mass may have increased with remarkable speed. Hydrogen and helium poured into the growing planet as long as the disk could continue supplying them. The new giant became massive enough to disturb the gas around its orbit and begin opening a broad gap. Material still crossed that gap through complex streams, but Jupiter was now changing the structure of the entire disk. Scientists do not yet know every detail of how quickly Jupiter formed or exactly how massive its first core became. Another proposed pathway suggests that a dense region of the gas disk could collapse directly under its own gravity. This disk instability model might create giant planets rapidly under the right conditions. For our solar system, core growth followed by gas capture remains the most widely used explanation for Jupiter and Saturn. Jupiter was not only becoming a planet, but also creating a smaller system of its own. A rotating disk of gas and solids surrounded the young giant, resembling a miniature version of the solar nebula. Within this circumplanetary disk, material gathered into moons that would later include Io, Europa, Ganymede, and Callisto. Those moons preserved a gradient from hot rocky regions near Jupiter to colder ice-rich regions farther away. As Jupiter exchanged gravitational energy with the gas disk, its orbit may have shifted substantially. Young planets can launch spiral waves through gas, and those waves can push the planets inward or outward. This process is called planetary migration, and telescopes studying distant systems show that large orbital changes are possible. Migration means that a planet's present orbit may not reveal the location where it first began to grow. One influential model proposes that Jupiter moved inward before reversing direction after becoming linked gravitationally with Saturn. This proposed journey is known as the Grand Tack because Jupiter would have changed direction like a turning sailboat. Such movement could have removed material from the region near Mars and helped explain why Mars remained relatively small. The Grand Tack is a useful hypothesis, but scientists have not established that this exact migration occurred. Saturn formed beyond Jupiter from its own growing core and captured a massive envelope of hydrogen and helium. It gained less mass than Jupiter, possibly because it formed later or because the supply of disk gas was already declining. Saturn also possessed a surrounding disk where early moons could grow, migrate, collide, and sometimes disappear into the planet. The familiar rings seen today formed much later or were heavily reshaped, so they are not a simple remnant of Saturn's birth disk. Together, Jupiter and Saturn became the gravitational rulers of the young planetary system. Their combined influence redirected planetesimals, altered growing planets, and sent waves through the remaining gas. Small changes in their masses and orbital relationship could produce large differences across the solar system. The final architecture was emerging through interactions that connected distant regions of the disk. Farther from the Sun, the worlds that became Uranus and Neptune faced a difficult race against time. Material was spread thinly across their region, and orbital periods were long, making collisions and growth less frequent. Their cores captured hydrogen and helium, but not enough to become gas giants like Jupiter or Saturn. Much of their mass remained in heavier substances, including water, ammonia, methane, rock, and metal. Astronomers call Uranus and Neptune ice giants, although their deep interiors are hot, compressed, and far from ordinary ice. Some models suggest these planets began closer to the Sun, where solid material was more concentrated and later moved outward. Their current positions may therefore record a later rearrangement rather than the exact geography of their birth. The formation of the ice giants remains one of the least settled chapters in the story of our planetary system. Between the growing realm of Mars and the orbit of Jupiter, countless rocky planetesimals continued circling the Sunday. There was enough material to create substantial bodies, including the object that would become the dwarf planet Ceres. Yet no full-sized planet formed there, and Jupiter's gravity was a major reason. Repeated gravitational disturbances increased collision speeds and prevented much of the region from merging into one stable world. Some bodies were shattered, while others were thrown toward the inner planets, the outer solar system, or interstellar space. The surviving population became the foundation of the asteroid belt, although it once contained far more material than it does today. Its asteroids are chemically diverse, suggesting that migration and scattering mixed objects formed at different distances from the Sunday. The belt is therefore not a destroyed planet, but a depleted and rearranged collection of ancient building blocks. As the giant planets grew, they also scattered icy planetesimals from the distant regions of the disk. Some traveled inward and carried water-rich minerals and carbon-bearing compounds toward the realm of the rocky planets. Others were pushed outward into remote orbits, where some would eventually join distant populations of comets. Many escaped the sun completely and became dark wanderers traveling between the stars. The solar nebula was now disappearing as radiation, stellar winds, and planetary growth removed its remaining gas. Once that gas vanished, the giant planets could no longer capture enormous new atmospheres or migrate through a dense disk. The next phase would be controlled mainly by gravity among planets, embryos, moons, asteroids, and comets. The system had become clearer, but it was still crowded, unstable, and filled with unfinished worlds. Among those worlds, the young Earth was still growing through collisions with embryos and planetesimals. Its surface was repeatedly melted, its atmosphere was replaced, and its interior continued separating into distinct layers. One future collision would become greater than the others and permanently change the history of our planet. From the debris of that encounter, Earth would gain a companion that still watches over its nights. The young Earth did not begin as a blue world, but as a growing sphere of rock surrounded by debris and repeated violence. It formed inside a crowded inner solar system where planetary embryos crossed paths and competed for the same limited material. Each collision changed its mass, rotation, chemistry, and orbit, making Earth the product of many separate worlds that no longer exist. The planet beneath us is therefore not a single ancient object, but a surviving mixture assembled across millions of years. As Earth gained mass, the energy of incoming objects was converted into heat deep within its growing body. Some impacts were powerful enough to melt vast regions, while radioactive elements continued warming the planet from inside. Pressure also increased as new layers accumulated, compressing older material beneath the weight of the forming world. For long intervals, much of the early Earth may have resembled a glowing ocean of molten silicate beneath a turbulent sky. Inside this molten planet, dense iron and nickel moved downward under gravity toward the center. Lighter silicate rock remained above, forming the basic separation between Earth's metallic core and rocky mantle. This process released additional heat and transformed the interior into a layered structure with very different physical properties. Earth's later magnetic field would depend on motion within its metallic interior, but that system was still developing. The material that built Earth did not all come from one narrow band around the Sunday. Gravitational encounters mixed planetesimals from neighboring regions, bringing together bodies with different temperatures and chemical histories. Most of Earth's mass appears consistent with relatively dry inner solar system material rich in rock and metal. Smaller contributions from more distant objects may have delivered additional water, carbon compounds, and other volatile ingredients. Scientists study meteorites to compare these ancient reservoirs and estimate which populations contributed to the young Earth. The evidence suggests a complicated mixture rather than a single source for the planet's oceans and atmosphere. Some water was probably carried within hydrated minerals, locked inside rocky bodies rather than arriving as free liquid. As those bodies melted, water and gases escaped from minerals and rose through the young planet. Volcanoes and molten surfaces released vapor, carbon dioxide, nitrogen, sulfur compounds, and other gases into an early atmosphere. That atmosphere was repeatedly altered by impacts, solar radiation, atmospheric escape, and gases rising from the interior. Earth was still unfinished when another planetary embryo approached on a path that would change both objects forever. This lost world is often called Theia, although scientists do not know its original name, appearance, or exact orbit. Theia may have been roughly comparable in mass to Mars, but its true size remains uncertain. For millions of years, gravitational interactions among embryos could have slowly shifted its orbit toward a crossing with Earth. The encounter was not planned by any simple clock, but emerged from the unstable motion of the crowded inner solar system. When the two worlds finally met, their relative speed was measured in kilometers per second. The impact released enough energy to melt enormous volumes of rock and vaporize part of both planetary bodies. Earth's surface became a global inferno as incandescent debris expanded outward into space. The collision may also have tilted Earth's rotation and changed the length of its day. Exactly how this happened depends on the impact angle, speed, masses, and internal structures of the two bodies. The leading explanation suggests that much of Theia merged with Earth while a fraction of material entered orbit. Some of Earth's outer layers may also have been launched into space and mixed with debris from the impactor. The result was a broad ring of vapor, droplets, and molten rock circling the damaged planet. This orbiting disk was temporary, but it contained the material that would become the Moon. Close to Earth, tidal forces were strong enough to prevent loose material from gathering into one stable body. Farther away, fragments collided, cooled, and began assembling under their own growing gravity. Within a surprisingly short astronomical interval, much of the debris may have collected into a single dominant moon. Smaller moonlets may also have formed and later merged, fallen back to Earth, or been scattered away. The newborn moon orbited far closer to Earth than it does today. It appeared much larger in Earth's sky and raised powerful tides in molten rock, oceans, and the planet's interior. Earth was rotating rapidly, perhaps completing a day in only several hours. Tidal interactions began transferring rotational energy from Earth into the moon's orbit. As Earth slowly lost rotational speed, the moon gradually moved outward to more distant orbits. That outward migration continues today, although the early rate was likely much faster and changed over time. The moon also became tidally locked, rotating once during each orbit, so the same hemisphere generally faced Earth. This familiar arrangement was the long result of gravitational friction, not the condition in which the moon first formed. Like Earth, the young moon was heated by impacts, compression, and radioactive decay. Large portions of its exterior may have melted into a lunar magma ocean. As this ocean cooled, dense minerals sank while lighter minerals floated upward and formed an early crust. The pale lunar highlands preserve remnants of that ancient crust, although impacts later shattered and reworked the surface. Samples returned from the moon contain chemical and isotopic clues that strongly connect its origin with Earth. Earth and moon rocks are remarkably similar in several isotopic measurements used to trace planetary source material. That similarity supports extensive mixing, but it also creates challenges for simple versions of the giant impact model. If most lunar material came from Theia, scientists must explain why it resembles Earth's mantle so closely. One possibility is that Theia formed from material already similar to the region that built Earth. Another suggests that the impact produced enough heat and mixing to make the orbiting debris chemically more uniform. More energetic collision models can generate a cloud of vaporized rock surrounding the combined Earth and impactor. Within such an extreme structure, matter could exchange between the planet and disk before the moon finally assembled. Scientists continue comparing simulations with lunar samples, Earth's chemistry, and measurements of the Earth-Moon system. The broad picture of a giant impact is well supported, but the exact sequence remains an active scientific question. After the collision, Earth was left with an enormous reservoir of heat and a surface dominated by molten rock. A thick atmosphere of silicate vapor, steam, carbon dioxide, and other gases surrounded the planet. As Earth radiated energy into space, the hottest rock vapor condensed and returned to the surface. The magma ocean slowly began to cool, although continued impacts could repeatedly melt parts of the young crust. Eventually, temperatures fell enough for stable layers of solid rock to form across much of the planet. These first crusts were not permanent continents and were likely recycled, broken, or buried by later geological activity. Earth preserves very little rock from this earliest age because the planet remained active and constantly transformed its surface. Tiny zircon crystals provide some of the oldest surviving evidence for conditions on the young planet. Some zircon suggests that liquid water and solid crust may have existed earlier than once expected. Their interpretation remains complex, but they hint that Earth could cool locally, even during a violent era. As the atmosphere cooled, water vapor began condensing into droplets and falling toward the dark surface. Rain may have fallen for long periods, collecting in low regions, while volcanic heat continued escaping from below. Some water returned to the atmosphere through evaporation, creating an immense cycle between sky, crust, and interior. Over time, persistent basins could hold oceans beneath a dimmer young sun and a very different atmosphere. Comets were once considered the main source of Earth's water, but the evidence points to a more complicated history. Many measured comets contain water with isotopic ratios that differ from the water found in Earth's oceans. Water-rich asteroids and primitive rocky bodies often provide a closer match, although no single group explains everything. Earth may have inherited water during its main growth and received additional amounts during later impacts. The same incoming bodies could also deliver carbon, nitrogen, sulfur, phosphorus, and organic molecules. These ingredients did not guarantee life, but they expanded the chemical possibilities available on the early Earth. Meanwhile, impacts remain frequent enough to reshape the surface and sometimes vaporize regional seas or portions of the atmosphere. The young planet could cool, be struck, melt again, and begin another cycle of recovery. The Moon recorded many of these impacts more clearly because it lacked oceans, weather, and active plate tectonics. Its ancient highlands became crowded with overlapping craters, preserving a partial history erased from Earth's surface. Large impacts excavated enormous lunar basins, some of which were later flooded by dark volcanic lava. Those dark plains became the lunar Maria, features once mistaken for seas by early observers. For many years, scientists described a distinct late heavy bombardment that struck the inner planets long after formation. Current evidence allows several possibilities, including a sharp increase in impacts or a longer decline from earlier violence. Lunar samples come from limited regions, making it difficult to reconstruct the exact impact history of the entire Moon. Future samples from additional locations may reveal whether the bombardment was sudden, prolonged, or divided into several episodes. While Earth and Moon evolved together, the remaining planets continued clearing their orbital neighborhoods. Some leftover embryos collided with planets, while others were thrown into the Sun or expelled from the solar system. Asteroids and comets were trapped in stable regions, unstable resonances, distant reservoirs, and temporary crossing orbits. The architecture of the solar system was becoming recognizable, but its final arrangement had not yet been secured. Far beyond Earth, the giant planets still held enough gravitational power to rearrange enormous populations of icy bodies. A small shift in one giant planet's orbit could disturb another and send consequences across billions of kilometers. The remaining debris would become the asteroid belt, the Kuiper belt, distant comets, and the scars left across every world. The final chapter would reveal how chaos faded into the planetary system that surrounds the Sun today. The solar nebula had faded, but the young solar system was still far from the quiet arrangement visible around us today. Planets had formed, moons were emerging, and immense populations of asteroids and icy bodies still occupied unstable orbits. Gravity now acted without the cushioning influence of a thick gas disk, allowing distant worlds to disturb one another more directly. The final architecture would emerge through a long period of scattering, migration, collisions, and the removal of surviving debris. Jupiter and Saturn were the most powerful objects in this unfinished system after the Sun itself. Their repeated gravitational pulls depended on how quickly they orbited and how often their positions returned to similar alignments. When orbital periods form a simple numerical relationship, the planets are said to occupy a gravitational resonance. A resonance can preserve an orderly pattern, but under different conditions, it can also amplify small disturbances over time. One influential family of models proposes that the giant planets once occupied a more compact arrangement. Beyond them stretched a massive disk of icy planetesimals left behind after the growth of Uranus and Neptune. Slow exchanges of energy between the planets and this distant disk gradually altered the giant planets' orbits. Eventually, the original configuration may have become unstable, transforming gentle migration into a much more chaotic rearrangement. During such an instability, the giant planets would have approached one another closely enough to exchange substantial orbital energy. Jupiter could move slightly inward, while Saturn, Uranus, and Neptune shifted toward more distant regions. The ice giants may have crossed paths or even exchanged their order before settling into separate orbits. Every close encounter would have redirected enormous numbers of smaller bodies across the outer solar system. Some computer simulations produce a system closer to our own when they begin with an additional giant planet. In those scenarios, repeated encounters with Jupiter throw the extra world beyond the Sun's gravitational control. The missing planet would then travel through interstellar space as a cold and nearly invisible wanderer. This possibility remains hypothetical, but it shows how survival may have depended on the loss of worlds we cannot recover. The timing of the giant planet instability is still debated and may have been earlier than scientists once assumed. Older models placed a dramatic rearrangement hundreds of millions of years after the first solids formed. Other evidence allows the migration to begin much sooner, while the terrestrial planets were still completing their growth. According to our current understanding, the broad process is more certain than its exact schedule or sequence. As Neptune moved outward, it encountered icy bodies that had formed throughout the distant planetesimal disk. Some were scattered inward toward the other giants, where additional encounters changed their paths again. Others were pushed outward, captured into stable resonances, or left on stretched and tilted orbits. The distant solar system became a record of Neptune's migration written into the arrangement of surviving ice. Today, many small worlds orbit beyond Neptune in the broad region known as the Kuiper Belt. This region includes objects with nearly circular paths, resonant populations, and bodies scattered onto much more eccentric orbits. Pluto belongs to a population whose members complete 2 orbits for every 3 completed by Neptune. That resonance protects Pluto from close encounters, even though its orbit sometimes carries it closer to the Sun than Neptune. Other resonant objects occupy different relationships, creating families whose orbital patterns reveal the history of planetary migration. A smooth outward movement would capture and transport bodies differently from a migration interrupted by sudden planetary encounters. By comparing models with observed populations, researchers test which ancient paths could have produced the modern belt. The answer remains incomplete because billions of years of collisions and disturbances have altered the original evidence. Neptune also sent many icy bodies into a more dispersed region called the scattered disk. These objects can travel far beyond the main Kuiper Belt before returning toward Neptune's neighborhood. Repeated encounters may eventually push some inward, where they can become short-period comets. Each comet entering the warmer inner system carries ancient ice, dust, and organic material from the era of planet formation. Other icy bodies were scattered so far from the Sun that passing stars and the Milky Way began shaping their orbits. Their paths became detached from the region of the giant planets and spread around the solar system in every direction. This enormous and distant population is known as the Oort cloud, although no telescope has imaged it as a complete structure. Its existence is inferred mainly from the orbits of long-period comets arriving from the depths of space. A distant comet can remain frozen in darkness for millions of years before a subtle gravitational disturbance changes its path. The tide of the galaxy or the passage of a nearby star may direct it toward the inner solar system. As sunlight warms the surface, buried ice turns into gas and carries dark dust into a growing coma. The brilliant tail is therefore a temporary display created when an ancient remnant approaches the star of its birth. Closer to the Sun, Jupiter continued shaping the asteroid belt through resonances and repeated gravitational encounters. At certain orbital distances, Jupiter's regular pull can increase an asteroid's eccentricity over long periods. These effects created depleted regions and helped deliver some asteroids onto paths that crossed the terrestrial planets. The belt that survived was a thin remnant containing only a small fraction of its likely original mass. Collisions continued inside the asteroid belt long after the main planets had reached nearly their final sizes. Some impacts shattered parent bodies and produced families of fragments following similar orbits around the Sunday. Other collisions exposed metallic cores, rocky mantles, or primitive interiors that had remained hidden for billions of years. Meteorites reaching Earth are pieces of this population and offer physical samples from many different early bodies. Some meteorites preserve material that never fully melted, including grains and inclusions older than any known planetary surface. Others came from differentiated bodies and contain iron metal or volcanic rock produced within ancient planetesimals. Their chemistry reveals the temperatures, water content, and radioactive processes present during the first stages of construction. Every fragment is incomplete, but together they preserve a history that active planets have repeatedly erased. The surfaces of Mercury, the Moon, and Mars also retain scars from the declining population of leftover impactors. Large basins record collisions capable of melting rock, launching debris, and reshaping entire regions of a world. Yet crater ages do not provide a simple calendar because old surfaces can be buried, recycled, or saturated by later impact. Scientists therefore combine crater counts, return samples, meteorite ages, and dynamical models to reconstruct the bombardment. The evidence no longer demands one simple and sudden storm of impacts across the entire inner solar system. Several populations may have declined at different rates, producing episodes that overlapped across long spans of time. Some impactors came from the asteroid belt, while others may have arrived from more distant icy reservoirs. The scars visible today are the surviving traces of a complicated transition rather than one perfectly understood event. As unstable bodies were removed, the surviving planets gradually became more widely separated and dynamically secure. Their paths settled into a common direction around the Sun and remained close to the plane of the original disk. The nearly circular orbits we observe are not signs of a perfectly peaceful birth, but the arrangement left after chaos removed alternatives. Countless other configurations were possible, yet only stable survivors remain to define the mature system. Each planet still carries evidence of the accidents and local conditions that shaped its individual history. Mercury contains an unusually large metallic core that may reflect early composition, extreme heating, collisions, or several combined processes. Venus and Earth grew to similar sizes, but their surfaces and atmospheres later followed profoundly different paths. Mars remained small, perhaps because its region was depleted before it could gather enough material to become another Earth. Jupiter preserved most of the mass it captured from the nebula and became the dominant gravitational influence among the planets. Saturn remained smaller but developed its own enormous system of moons, rings, and captured objects. Uranus rotates on its side, possibly because of a giant collision or a complex sequence of early gravitational interactions. Neptune became the distant sculptor of the Kuiper Belt and the outer boundary of the major planetary system. Moons also record the environments in which they formed, migrated, collided, or were captured by passing planets. Regular moons commonly orbit near a planet's equatorial plane, reflecting their growth within surrounding disks. Irregular moons follow distant and tilted paths that often suggest capture from populations of passing planetesimals. The Moon remains exceptional because its origin was tied directly to a collision that transformed Earth itself. Scientists reconstruct this history by combining information from telescopes, spacecraft, laboratories, computer simulations, and samples returned to Earth. No single source of evidence can reveal the entire sequence because every record has been altered or preserved selectively. Meteorites provide ages and chemistry, while planetary surfaces show the physical results of impacts and geological evolution. Orbital patterns reveal invisible gravitational history, allowing modern positions to carry clues about ancient migration. Samples from asteroids can preserve fragile substances that are changed or destroyed during passage through Earth's atmosphere. Lunar material provides evidence from a world that shares Earth's neighborhood but lacks its oceans and active plate tectonics. Future missions to comets, moons, and distant icy worlds will test whether our current models explain their hidden interiors. Each new measurement can confirm part of the story while forcing another part to be reconsidered. Young planetary systems around other stars offer another way to study stages that our own system completed long ago. Telescopes observe dusty rings, gaps, spirals, growing planets, and disks being cleared by radiation and stellar winds. Older planetary systems reveal an astonishing diversity of worlds arranged in ways unlike the solar system. Some contain giant planets near their stars, tightly packed rocky worlds, or planets moving on highly elongated paths. This diversity shows that planet formation follows common physical laws without producing one inevitable final design. Small differences in disk mass, temperature, chemistry, stellar environment, and timing can lead to entirely different systems. Our solar system is therefore neither a universal blueprint nor an inexplicable exception. It is one surviving outcome of processes now unfolding around young stars throughout the Milky Way. Nearly all of its matter began inside a cold cloud that no longer exists in any recognizable form. Gravity gathered that cloud into a star, a disk, countless small bodies, and finally the worlds orbiting the Sunday. The planets appear permanent on a human time scale, yet every one of them carries the memory of movement, destruction, and survival. From ancient stardust to Earth and Moon, the solar system remains a quiet monument to the creative power of cosmic change.